Okay, we're going to look at now the situation when the population parameters are unknown. But let's first take a look and review of what we did when we knew the population parameters. For example, with the R-score, we knew that the population mean, that's set by the Ministry of Education at 25, with a standard deviation of 5. And we also know that X, students' R-score, random variable, follows the normal distribution. And then what we did was we determined the standard error depending on the sample size. For example, we had 6 students randomly chosen. We were calculating the average of the 6 students. And then we used the confidence interval formula with the standard error to say that, well, we'd expect that, for example, at the 95% level, we'd expect that 6 students would have an average R-score somewhere between 21 and 29, for example. And we can draw it graphically this way. We had the upper bound and the lower bound with 21 to 29, 2.5% above, 2.5%. This is all assuming that we have the parameters are known. And our current situation is like landing on a planet like Mars or somewhere. We're taking a sample of the temperature or air pressure. Well, we don't know what the population mean is. We don't know what the standard deviation is of the population. We don't even know if this random variable, this number we're measuring, is even normal. We don't know what the distribution is. So we don't know anything about the population. So in this case, we can't really determine the standard error because this sigma x here is unknown. And we can't construct the confidence interval because, well, the sigma x is unknown and the population mean is also unknown. Now, to get this straight, the critical z, we can still look that up in the table. That we can know. And of course, we'll know the sample size because you know how many times we've drawn from the population. But these two parameters are simply unknown. So we're kind of stuck. We can't create a confidence interval around the population mean because we simply don't know what the standard error is. And we can't create a lower bound or an upper bound. So what are we going to do? Well, we can rely on something. We have a sample. So first of all, we can use the sample mean to estimate the unknown population mean. You notice something here. I put a little hat on top of the Greek letter for mean to indicate that this is now an estimator. So I'm going to use the Latin letter x, our sample mean, to estimate the population mean. And I'm going to also use the sample standard deviation, s, to make a prediction, once again, of the population standard deviation. So we can now calculate an estimated standard error. We know it's not exactly correct, but we can call it an estimator of the standard error. I could write it like this. Indicating that it's the estimated standard error. And I can now use this to create a spread for the sample mean. We can create a confidence interval. Notice what we've done here. I've changed the x bar, changed the mood for the x bar sample mean, which is known, possible to calculate. I've changed also the known sample standard deviation for the population standard deviation. And now I can create the upper bound and lower bound not around the population mean, but around the sample mean. In this case, what we can say too is that we would expect that there's a 95, for example, if we do it at the 95% level, we can expect that the population mean will fall within this new confidence interval we've created, bearing in mind that the population mean is actually fixed, and what's varying is our sample mean. So while we know that the target is fixed, we've sort of created our upper bound and lower bound confidence interval around the sample mean that we've calculated.